No, it took me like halfway. It's like basically when I came in, it took me basically almost the last break to realize that.
All right, I'm really sorry to interrupt you all, but we should get started. It's 1 p.m. So, from redox reactions, what do we remember? What is a reduction and what is an oxidation?
Reduction is more bonds to hydrogen.
Yeah.
And oxidation is more bonds to oxygen.
Yeah, that's basically it. What kind of compounds can we reduce, and what kind of compounds or functional groups do we oxidize?
Reduce carbonyls,
Yeah, and then we oxidize.
alcohols.
Yeah, we oxidize alcohols. And there's different strengths of reagents which you can use to do that. And then that's going to give you a different product based on what you use. The answer sheet's on Canvas, and I don't want to spend too much time like redoing this. So I'll just demonstrate with some problems. Okay, so first I wanted to mention this question yesterday. We said which reagent would be used to perform the following transformation, and in this reaction we had a ketone that got oxidized to a secondary alcohol. But when you get problems like these, which I think are fairly common, where they give you the condensed formula, you just have to look for what other functional groups are present. So in this case, we had an ester present, and you can tell that by the formula. So I didn't learn the condensed formulas for functional groups until like a lot later in the class, so I should just give them to you now. So when you see a CO2 something and then an R group on either side of the CO2, it's going to be an ester. If you see an RCO2H, that's a carboxylic acid. Oh yeah, a ketone. So in a ketone, how do you differentiate a ketone from an ether? Because they're just an O with R groups on either side, right? So for a ketone, you have to know that this carbon bonded to the oxygen is just going to be a C. But if you have an ether, this carbon bonded to the O is going to have hydrogens on it. And then an aldehyde is my favorite because it's just CHO. I'm missing any. Oh yeah, ether is just. Then the ether is not going to have any, it's going to have hydrocarbons right next to it. Whereas with the ketone, you just have this single carbon with no hydrogens. I think that's all the important ones. So yeah, just keep an eye out for all of those, and it's good to memorize. But for this problem, we oxidized the ketone and the ester was unaffected. So we know we had to use what kind of reducing agent?
Sodium borohydride.
Yes, we had to use sodium borohydride because that's the only weak one. If we had LAH, it would be a strong reduction. So the ester would get reduced as well. But that didn't happen in the reaction, so we know we had to just use A. And for all of these redox reactions, maybe it's good to know the mechanism, just be aware of it. But all you really have to know is what functional group gets turned into what by what reagents. So just a bunch of equations, like primary alcohol plus these oxidizing agents equals an aldehyde or a carboxylic acid. And I'll write that out and post it eventually. But that's how you should approach these. And then it's really not that complicated. But let's try these 4 problems up here. So the whole point of this problem is to reduce all the following compounds. So for the first one, what do we have?
Is it lactose?
It is a lactone, but a lactone is a kind of cyclic ester. Since it's an ester and we want to reduce it all the way, what do we have to use?
Lithium.
Yeah, we have to use the lithium LAH. And what does the acid on the bottom do? Yeah, it just protonates it once you open up the carbonyl. So if anyone remembers how to do these reactions, do you want to give this one a try?
I will.
Okay,
I need a mark.
but do not use marker on this board. There's like that weird pen thing up there.
Oh, so do it on that, okay.
Or you could do it on the boards on the side.
Well, this one is.
If it works, use that.
It's like open
Good
three
job.
different applications.
Had to pay for one.
Got us in the first,
I'm actually going to know.
Looks nice.
Oh, wow.
No, I'm good.
You sure about that one? Yes, that is right. Good job. Do you want a sticker? No stickers? I have so many.
Only if you have SpongeBob.
Huh?
Only if you have SpongeBob stickers.
Next week I'll have SpongeBob stickers. Yeah, what do you think I have?
Do you have a gold star?
No, no gold stars. No SpongeBob.
I'm out, I'm folding.
We just have lame nerdy sign stickers. So if that works for you.
That's pretty cool. If they have pure mechanism stickers, I'll take it.
They not a market for those, but
No.
that's what I want. And then in the process, we added 2 hydrogens to the carbonyl.
No, we didn't even, we don't.
So does anyone know why we added 2 total hydrogens to this carbonyl?
They needed it.
And why?
Yeah.
Yeah, I hated it. Because the oxygen in the ester is like a leaving group, so then the hydrogen, once we do one mechanism, like one reaction, then we gotta do it again. That's why 2 hydrogen.
Yeah,
To create alcohol.
yes, to create the alcohol, because once you attack, well, once we do the first attack, it opens up into what functional group?
Is it an aldehyde?
Yeah, it opens up into an aldehyde. Let me find an example. So like here, when we attack the carboxylic acid, you added a hydrogen, the oxygen left, and then now you're left with an aldehyde. So same idea here. After the first hydrogen gets added, you have an aldehyde. An aldehyde is still a carbonyl, and when you have a carbonyl, you can attack it once more to reduce it. So that's where hydrogen number 2 came from. After your 2 hydrogens are added through addition, you're going to have an acid-base reaction, and then the oxygen ions are going to get protonated by the acid. And that's it. So does anyone want to do the next one? Which was the
The right or the bottom?
bottom?
We even have it.
Go for that sticker.
That look right. There's no mechanism. Oh, wait, no, I'm thinking about it.
Either way.
I don't have one. I don't have that.
That's fine.
You're lying. We did one problem. You did your part. Congratulations.
Is that why you, is that why you volunteered? You wrote the catch.
Could you use another one also?
Participation.
Yeah.
NADH4.
Yeah, so it's a ketone, so you can use either one, and you'll get the same product.
I just need to draw a methyl.
Whatever. Is there a leading group? So it would break.
What do I have that? What bottom one? I do have the bottom. I know I do have, so I just drew. There's a method with the bottom.
Like the final answer.
Do I have the page?
Yeah, it's fine.
And then there's a H2.
I think I went on the board and I struggled.
Yep. This is.
There's still more 20 minutes on.
That's perfect. When you like stay here.
You really wanted one, I asked like you didn't care.
Not the
whole
Pick from the Ziploc bag. Okay, so what happened here, so what you really need to recognize with this one is that you have a ketone and you're trying to reduce it. Since it's a ketone, it can be reduced by anything, so we can choose any reagent, either lithium or the sodium one, and you're gonna get the same result. So what you should recognize is that every time you have a ketone in a reducing agent, you get a secondary alcohol. So you should just be like, oh, we're trying to reduce the ketone. Cool, we can use anything and we're gonna get a secondary alcohol. But if you like using the mechanism to get to your answer, that works too.
Doing the next one?
Yeah. You want to?
Sure.
I can do the last one.
Is this still reduction?
They're all reduction, yeah. And other colors.
Sounds like it.
Yo, do NABD4.
BD? Okay.
Yeah.
This is just.
Better one.
Hold on, I got the back.
Oh, no, we erased your word.
No. Right.
No. So is the last hydrogen gonna come from the NABD4 or the acid?
Yeah.
So in case for regional selectivity, does it form the RMS product?
Oh, yeah.
Is there like an enantiomer?
Yeah, it's
Is
just
it
gonna
like
be
an
a,
SN2 reaction?
no, it's not SN2, it's just like, I don't know, nucleophilic addition.
No.
So we're just gonna get a racemic mixture. Because right now it's like planar, there's no existing stereochemistry. When you add it, it can like do whatever it wants.
Makes sense.
There you go.
It's a-
So when you have NABD4, you're just gonna have to replace the oxygens that you reduce with deuteriums, the hydrogens you reduce with. So over here, during the reduction, we added 2 hydrogens because they came from the LiAlH4. Over here, since we have deuteriums, the hydrogens that get added to the carbonyls are going to be Ds.
You just drop the final answer.
And in this case, it's a ketone, so only 1 deuterium gets added. When you protonate the final oxygen, remember the protonation step happens from the acid, not the reducing agent. And since the acid is H3O+ and not D3O+, we just have an OH. All right, the last one.
Oh, wait, do it?
Yeah.
Is this the same one? Yeah, the first one.
Look at that. You take this one. Yeah. I'm literally gonna have to use that one. It's like blue, it's just like. What? I'll put this.
Yeah.
Every time I have flames on my computer. Right, that's decal, that's different.
Like one of these. Over it, right on the back window.
So in this case, we had an ester. Actually, do you want to try something?
Which one?
The thing you just did.
You mean explainer?
Yeah, you got it.
Sure.
I know.
I'll take a sticker later.
What?
No.
Okay, so we have a ester, so we can only use the lithium reactant, so we do that. It's gonna kick that bond is now gonna break, and we end up with this. So we have the oxygen, we have our added hydrogen, and then because we have this oxygen right here, this is like the leaving group. So when this is going to try and bond here, that's gonna then leave. And then, so like technically we get an aldehyde up here, and then when the extra hydrogen gets added, we get this. And then with the acid right here, it protonates and we get an alcohol here.
Nice. You want another sticker?
You can get the first.
Oh, now you get two. So when you have esters, because of that leaving group, you reduce the first time and then you get an aldehyde. Once you have an aldehyde, that's a carbonyl again, so you can reduce it a second time. That's where you get two total hydrogens added, so it goes all the way down to a primary alcohol.
So does the leading group like ever, like, well, would that specific leading group like ever do anything, like react with anything, or does it just kind of float? Would it protate? I guess that's.
Oh, yeah.
Yeah, I
Would-
guess it
would
would
the-
just like float around and get protonated.
Okay, okay.
So would you put both of those, like, would you put the benzene with the byproduct? Yeah, with the byproduct in there?
I mean, you could, but like no one really cares enough to do that.
Do you always protonate naturally?
I mean, if you have something to protonate, yeah.
Oh,
I
See,
know,
that's the
man.
thing.
we, so I asked about that last time, and today he says you can assume that it's either water or acid.
Okay.
Yeah, he said assume everything now. Yeah, my bad.
So for like certain reactions, I guess, like for certain reactions like alcohol synthesis, I think you have to worry more about where the protonation happens, but in stuff like this, I guess it doesn't matter.
Okay.
Okay, so now it's time for Grignards. Yes, Grignards. Up until like last week, I used to spell them Grignard.
Grignard.
This
Yeah.
sounds like some Harry Potter.
No, it sounds like where Thor is from. Grignard.
Oh, yeah.
Okay, so when we have a Grignard reagent, is it gonna be a nucleophile or a base or both?
Both,
Yes, it's both. Why?
because it acts as a electron pair on its carbon.
Yeah, it has an electron pair to donate.
Yeah.
And that's what nucleophiles and bases do. They just do it for different things. When you have a nucleophile, you're using the electron pair to create a new bond. When you have a base, you use that extra lone pair to take a hydrogen away.
I have a question.
Yeah,
With the Grignards reagent, is it only MGBR or can it be like MG with like another halogen?
I think it's
Iodine.
any halogen.
Yeah,
And then you can also have this, you can just have a lithium there, it does the same thing.
You said, yeah. you
Oh,
said
that's the one we
anything-
drew through, right?
Yeah.
You said anything before I.
Oh, okay.
The lithium for, that's a more ionic one, right?
Oh, I don't know, I just know they do the same thing, yeah.
That's the same with like Na, right? If we had Na there, because like for an alkyne, Na.
Yeah, I guess it's the same, it's just spectating there to stabilize the charge, it's not covalently bound.
Yeah.
Are we gonna have to know Gilman's?
I forgot what that is.
It's weaker.
Yeah, right, that's what.
It's what?
It's weaker than MGBR a lot.
Yeah, this is like.
I guess.
Oh, good, in class?
Say nothing about it.
Yeah, that's Gilman, yeah.
Wait. Did he put it in his lecture notes?
No.
Oh, did he don't? Yeah.
No.
Stop making me.
I told you.
No,
Nelly
it's
down.
different.
Go into the dumbest.
It's
dumb
R2
Okay.
copper lithium.
Where'd you go?
There is
Oh,
lithium in it.
yeah, okay, I remember it.
Yeah.
Don't, no.
No?
Don't.
React.
Just don't.
Okay, so in what cases does a Grignard react as a nucleophile and in what cases does it act as a base?
I know nothing. Yeah.
Does it act, does magnesium act as a nucleophile when it enters right there?
When what?
Does magnesium act as a nucleophile when it enters into the bromine?
When it squeezes
Oh.
itself.
I don't think so. I mean, I don't know how that happens. I don't know like what mechanism it goes through.
If there's an acidic hydrogen that's stronger than carbon hydrogen bond.
And as long as you have an acidic hydrogen, that works.
Yeah.
So it's gonna act as a base when you have an acidic hydrogen. And it acts as a nucleophile when you have an electrophilic carbon to attack. So like carbonyls, basically. So we make Grignards by starting with an alkyl bromide or an alkyl halide. And, okay, this is reversed. It should really just be this. And then you boil magnesium with ether with the alkyl bromide, and then the magnesium just sticks itself in the middle. So after this, oh, it's already there. After you boil all this stuff together, you get your Grignard reagent, which is this. And when you see an MGBR, you can basically just cross out the MGBR part and just assume that it's this carbon that has a negative charge on it. So it's like the same thing as a sodium spectator ion, just cross it off and slap a lone pair on it.
No mechanism needed for that, right?
No. Now that you have this, we know that carbons are really bad at holding charges and they're super unstable. So a Grignard, since it's super unstable, it wants to use that lone pair and get rid of it by either attacking an electrophile or attacking a hydrogen. So when we have a carbonyl, what is a property of this central carbon?
Oh, it's
Partial
positive.
positive bond.
It's partial positive.
Yeah.
So the partial positive means that it's lacking electron density. Because there's less electron density around it, we can send our Grignard to go in and donate the lone pair to it, right? And it's the exact same principle as we did with like redox reactions. You're just sticking stuff onto the carbonyl.
So it creates the primary alcohol.
Tertiary.
Yeah.
Oh, true, yes.
So we just replace the hydrogen with whatever is
Yeah.
attached to the Grignard.
Yeah, okay.
So the mechanism for this. Yeah, so we have a CH3 NGBR, which is basically just one methyl with a negative charge on it, which is extremely unstable. It's like terrible, which makes it a really strong reagent. So we just have, we should draw this, just like a dot with a negative charge. Yeah, so you just have one carbon with a lone pair on it. It's going to go and attack the electron unrich, electron poor carbon. And then you just get a new bond with methyl attached. So this is gonna unfold, the double bond goes up, and then you get this. With your new methyl.
Not to be picky, because I just like looked back at your notes and I read it down. Can you just change that down to a C? CH3.
Oh, sure.
Or CH3.
So we get this as an intermediate, and then we have H2 as our second step. So what happens? Yeah. So our final result is just what?
Tertiary.
Yeah, we just get a tertiary alcohol. It's that simple. I love Grignards. There's
Science is amazing.
yeah.
And the H contains H2O.
Yeah.
Where does H2O go?
One more thing to note, I doubt you'll ever get tested on this, but I was like confused about this for so long because I was like, oh, the Grignard and the H2 is on the same like arrow here. That means they're like all mixed together. But the Grignard comes first, and then after you finish reacting that, then you add the water or acid to protonate it. You
Yeah.
can't actually mix the Grignard in the water because it's gonna ruin the whole thing.
That being said, he likes to just put the Grignard reaction without the acid, and then you're just supposed to know that it goes through completion.
That's just on the book, that probably won't be on the Wiley.
Oh, he was on the Wiley.
Oh,
I mean, of course, it's the why everything.
Yeah. I had a fun time with that.
Wait, what did you say was on there? Like, that it goes to completion?
Yeah,
That
It's
just
gonna
protonates at
go
the end.
all the way.
yeah, all the way. Or like it won't have like one or two equivalents if it's like an ester or something. You just assume everything.
Yeah,
It's great.
yeah.
But I have a nervous breakdown during the steps.
We all have nervous breakdowns. We can't do anything about it.
I mean, he said he wasn't curving anyway, so.
And he has like 1 point. Great.
Yay! The curse is 1 point.
Oh, no, there it is.
No, but, okay, by the time it's like the end of the semester, he feels really bad because everyone's failing, so he gives you guys like extra credit.
Oh, really?
Yeah, but it's really hard, and no one like
Yeah,
gets
that's what happened
points.
with Tito.
He was like, so no one's taking off throughout the whole semester.
I took two.
Okay, so now that we know how to do Grignards,
Yeah, the midterm curve. That was insane.
now that we know that Grignards are similar to redox reactions, what do we think is gonna happen when we have an ester?
It's gonna kick off the.
Yeah, we have a leaving group, so it's going to attack twice.
You guys,
So, yeah, I'll just draw this one too. So we cross out the MJBR, add our negative charge, and then we know it's just gonna go ahead and attack the carbonyl.
Not to cut you off, but we know just close to the extra point.
Yeah, oh, really?
Yeah.
So how long is it up for?
Yeah, 1 to 2, the 8.
Okay.
11:59.
Okay.
Guess we'll string
In
it.
4 days.
Yeah.
Like 4 days.
I guess
Girl.
Wait, that's Saturday.
So remember in the first attack, when you add that thing to the carbonyl, the leaving group is just gonna be gone. So we have this now. We have an ethyl instead of this thing.
I thought it was a ketone.
Yeah, so then the lone pair from this oxygen comes back down and we get a ketone. Now we have another carbonyl, so what can we do?
Do it again.
Use another approach.
Yeah. So the ethyl Grignard comes back, attacks again. And can we attack this anymore?
No.
So what do we do now?
Protein.
And we're left with another tertiary alcohol.
So we know that it goes all the way to an alcohol because it's really strong.
Yeah.
Are there weak ones?
Grignards.
Well, other than the Gilmans, but we're not gonna do that.
I don't think so. I think it just goes all the way.
Yeah, the LII is like the same exact thing.
Oh, okay.
So for the second one, we have the same idea. We have another ester, but it's cyclic this time. And we also have this really annoying nucleophile. We have a phenyl magnesium bromide. So it's just a phenyl with negative charge on it. So what do you think is the end product is going to be for this? We have an ester and we have a nucleophile. How many times do we add the phenyl?
Twice.
Yeah. So we can skip the mechanism and just add the phenyl twice to the carbonyl.
Can I just put pH on it?
Yes.
Okay. It's gonna be a pho.
And since it's cyclic, when this group leaves, this oxygen is still going to be attached to the molecule, but this bond is just going to break.
Oh, then it's gonna get pronated.
Yeah, and then it gets pronated and then you take this thing and then, well, you don't even have to draw that stuff, just assume it gets pronated.
Yeah.
So you're drawing the final product anyways.
Does the alkoxide, when it does break off, since it's still floating in the solution, does it get pronated as along with the actual product?
Yeah, it gets pronated simultaneously whenever you add that acid.
Yeah.
So for this one, what kind of carbonyl do we have? So how many additions are we gonna do?
One.
Yeah. And what's that gonna give you?
Tertiary
Yeah,
alcohol.
another tertiary alcohol.
Yeah, another tertiary alcohol. You're basically just replacing one of these double bonds with whatever is attached to your Grignard.
Yeah. it's just not- that takes-
And in the last one, what do we have here? Yeah, an ester. So how many additions do we do?
2,
Yeah, so the final product is gonna be what?
another tertiary alcohol,
And then what are the two groups?
the phenyl or benzyl.
Yeah, we're just gonna have tertiary alcohol with two phenols. That's all there is to it. It's so nice.
Very.
Next.
So here's another question. What is a product of the following reaction? And here we have an ester with a phenol skeleton.
I think somebody asked something in the chat.
Oh.
Awkward.
Oh, good question. They,
Just do.
yeah, they literally just do. Now, the whole complex is really unstable with the two phenols attached. The two phenols attached to the same carbon. That is like a very,
Guys,
all right.
Oh, got it.
Thank you. So, it's really bad sterics, but it still happens anyway. Like the Grignard is still gonna do the reaction, even though there's so much steric hindrance because the Grignard is that unstable and it wants to be stabilized that badly. So despite how ugly the product is, it's gonna make itself work because it has to.
Just does.
Exactly.
Just does it.
My questions.
Yep. Just does it.
Okay, so for this one, we have an ester and a phenol. So what do we think happens?
It breaks open the ring.
Yeah, but remember the second function of a Grignard.
Oh, it's, yeah.
Yeah, is there an acidic proton on this molecule?
Yes.
So what's it gonna do?
it's gonna interact with that first.
Yeah, it's just gonna do an acid-base reaction and take this proton.
And what would that look
I draw something, yeah.
Just cross out the.
My line.
Yeah, but it's not. I'll do it.
Or what I do for like the benzoic groups, to make it easier, I just draw the circle in the middle, so I don't have to draw each line.
Yeah, these are 3 lines are the problem, it's the hexagon.
Yeah, the hexagon messed me up too.
It's just so unpleasant.
You kind of like make a hexagon, you make a circle that like has enough sides on it.
What? Like a really bad caveman circle.
Yeah, I was gonna say, how does a circle have sides?
You got the
That's the
line.
purpose of a circle.
If you got 3 lines, so you are still like, oh, that's the benzoic.
So it's text that only.
And if we had no OH on the bottom, what do you think the product would be?
But if you don't have the alcohol.
Yeah,
It would be
Oh, well,
two
then
alcohols.
the top part just gets.
Yeah.
You get 2 metals at the end. And
Yeah.
OH.
exactly. So we get another tertiary alcohol because we did 2 additions to the ester. And this just turns into an alcohol.
Yeah, the Grignard, to the one on the right. Okay, continue.
Yeah, when.
Yeah, if you like did this reaction to completion and got this as your product, then you could do another Grignard again.
Like three.
Yeah, and then, yeah, you would need 2 equivalents, or 3, you're right.
Yeah.
And then you would get this product.
You're
So,
missing the metals on the answer.
so for that, like what you said, would we assume that it's in Texas or?
I don't think so.
No?
I wouldn't put that much thought into it.
Yeah, because now I don't know what to assume.
Yeah,
Yeah, especially if you draw your own knowledge.
Yeah.
Do I draw intermediate stage?
Oh, that's true, because it'd be multiple choice anyways. Okay.
If it is,
and if it's like in excess, if he indicates it, then maybe, but
Otherwise, no. Okay.
Way.
Oh, true, yeah. the whole one makes it yours.
all right, so here we have a bunch of multi-step, well, one multi-step reaction. These were like his favorite last semester, so it's good practice. But to get A, we reacted an alcohol with PBr3. What does PBr3 do to alcohols?
it replaces it with a bromine.
Yep.
Exactly. So product A looks like what?
1 bromo hexanol. Cyclohexanol.
Yeah.
Cyclo,
Hexane.
yes, thank you.
So cool. We have that. And now we have Mg over ether. So what happens when we react that with an alkyl halide?
It goes in between.
It becomes Grignard.
It will kick off with the,
What did I say?
or the, oh,
You're
and
not-
then- never
Yeah.
mind.
It does see like focus ionic thing.
Oh, yeah.
So now we have a Grignard reagent and we also have an ester. So what happens?
It breaks the
The same
ring.
thing.
Yeah, it breaks the ring. And then how many times does the Grignard get added to the carbonyl?
Twice.
Yeah.
No, there's 2 R's.
So in our final product, we're gonna have 2 alcohols. What kind of alcohols are those 2 gonna be?
Tertiary.
One's tertiary, one's primary.
Yeah.
I'm not gonna attempt to draw the interconnection.
Yeah.
Every time we drink it.
Can I put B? Can- Just put,
We'll do R.
Yeah, I like that.
or, yeah. I'm trying to think of like how I can draw a text. Like, isn't it
Yes.
No, because there's no double bonds in the middle.
Oh,
R is a lazy man's compound.
And then we have this giant problem, which has a bunch of reactions from our past chapters. So for the first, yeah,
So going back, it would make two of those R groups based on that, right? Yeah.
yeah,
It'd be two cycles, right? Not the R, that's what you're referring.
the R represents the cyclohexane, yeah.
Okay.
So the first time we added it, the oxygen part of the ester left, and then the second time we added it, it added to like aldehyde. And then after this, after it becomes a tertiary alcohol, you can't add anything else.
So just to, like have it stick on my mind whenever we have a situation with a ester or a cyclic ester, or cyclic ether, it would be, we would have to do that reaction twice, right? Like it would be like those two R's with the hydrogen.
If you have a leaving group, you do it twice. It's the same with reduction. And then if you have no leaving group, like if you have an aldehyde or a ketone, it only happens once.
So whenever there's just the two oxygens, double bond, single bond. It's gonna be two.
So I literally just memorized like ester, you just add it twice. And that's like all the thought you need to put into this chapter.
Next time.
Sorry for my name.
So for reaction A, what's happening?
Oxidation to a ketone.
Yeah, we're going from an alcohol to a ketone. So what set of reagents is going to do that?
B.
What is B?
An oxidizing agent?
Yeah. Okay, well, that's the answer. Thank you.
Yeah.
Well, it has more oxygen, so.
But there is no other oxidizing agent. So like if we could use any since the ketone, but
I was asking what the name of it was.
oh, I think that's Jones reagent.
Yeah.
Oh,
I think it is
is
just.
the sodium one the Jones or is the H?
Jones is like the crow, it's like,
No, they're all crow, but there's one specific
No,
crow
that's
that's
not
Jones.
Jones. Jones has H's.
Yeah, that's what it's, I
This has NA.
I'm gonna Google.
that's why I was confused.
I actually don't know.
Oh, yeah, no, you're right. H2,
Yeah.
CR2, O4, Jones. What is that?
Yeah.
I don't think it has
everyone's
a name.
It doesn't, it's only two of them have names that we're concerned with, the Jones and the Swern. The Swern is the COCl2 over DMSO, and NET3.
So it has DMSO in it.
Yeah, DMSO is the solvent, and on top you have the COCl2.
Anytime we see the chromate, we know it's the same as like the Jones reaction.
Is it
Bromate,
supposed to
Yeah, I
be
think
Jones?
so.
Yeah.
What?
The PCT one?
No, PCC is very different from the chromate. PCC is weak, so PCC does the same thing as Swern.
Right.
And then all the crows do the same thing.
Okay.
But the crow with the H's is called Jones.
This isn't Jones.
No, this is like some miscellaneous agent.
But it's
Sodium.
still oxidated.
Yeah,
Okay.
it does the same thing as Jones, we just didn't give it a name. So we have a ketone, and then what does it get turned into?
The ketone or the,
And alcohol.
oh, okay.
Yeah, it gets turned into an alcohol. And what can we use to make that happen?
Grignard.
We can use a Grignard. So what's the only Grignard in the answer choices? Yeah,
I'm gonna name my son that.
so after we get an alcohol, we dehydrate it, and Dr. Rose told me he like wasn't concerned with dehydration, so don't worry about that, but I think it's deep.
Oh, like
She was just added into my life.
Yeah, it's gonna be an acid catalyzed dehydration, but I had it on my last worksheet and he was like, no, we don't do that in this class. And I was like, okay, so yeah, don't worry about that. So now we have an alkene and we're going from an alkene to an epoxide. What two reagents do that?
C
The C
and E. C.
Oh, no, I meant in general. There's no,
Uh,
yeah, C is the only one here. But in general, we can have, actually it's only one reagent.
Yeah.
Yeah, because we have a peroxy acid that adds an epoxide.
That's it.
And you can just have like a general miscellaneous peroxy acid, or we can use the one with the name, which is MCPDA.
Why does it, when they show the epoxide, it's always facing towards us? So like,
I mean, you could make it dashed, same thing.
it doesn't matter, it's just,
No, because like, either way you flip it, it's the same.
I thought it was based off the chair, like, that's the way they put it in equatorial.
If there's like another group present, yeah, but there's nothing else here, like on the other carbons.
like, I mean, it could be at from either side, right?
Yeah, as long as it's thin.
Okay.
But once again, do not put thought into that. It's,
Just take it as it is.
yeah. And then we go from an epoxide to a diol. So what's these epoxides? E, yes, that's an acid catalyzed cleavage.
Or F.
E, isn't it E?
Yeah, F also does it, that's base catalyzed. So how do we know which one to use?
The one that has.
Yeah,
More
why?
oxygen?
SN2.
More oxygen. Like, wasn't that the one with like 4 or more, you picked that one?
Yes, we're oxidizing,
Yeah, sorry.
but we're just breaking epoxides right
I
now.
just remember saying that like NaOH is like a double no, like never used it.
What?
Oh, maybe it was for something else.
No, you said.
Oh, that was for
like
ether
a baby
synthesis.
base.
Oh, okay.
He said, let's try to come up with more
Something
intelligent
better.
bases.
Something harder.
Yeah.
Yeah, we don't use NaOH for making ethers, but we can use it for breaking them, I think.
Okay.
But the way you can tell which reagent or like which way you catalyze the cleavage is to see where the nucleophile got added. In this case, we just look at which carbon there was an inversion at. So when you break an epoxide, you do it through an SN2 reaction, and then your nucleophile gets added to whichever carbon you attacked. And since you know it's SN2, there's going to be inversion. So since there's inversion on this carbon, you know we went in and attacked on this side. And this side is the more or less substituted side of the epoxide.
More substitute.
Yeah, and since it's more substituted, which reagent do we use to attack there? Yeah, so acid catalyzed goes from tertiary to secondary to primary.
Oh, right.
So if there was no inversion, it would have been F.
Well, yeah, but the inversion would have happened here. And then this one would have stayed the same. So you look at which side gets the inversion. And that tells you which side you did the attack.
And then the base catalyzed does the opposite.
Yeah.
Primary,
Yeah.
secondary.
Okay.
why does acid tertiary, secondary?
Because the whole mechanism for acid catalyzed cleavage is SN1 like. With SN1, you want the more stable carbon. Alright. And then if you have a base, you just go straight in and do an SN2. So that's why you go from the least to most substituted.
True.
Yeah.
It's gonna be a struggle.
So for all of those reasons, because we attack at the more substituted side, we know we use an acid catalyst, and the only one that has that is E. Okay, so that's a nice summary of all the reactions. It's, yeah, there's like 2 minutes.
All right.
Not doing anything else.
I change it all the time.